Hello, welcome to another module in this massive open online course. So, we are looking at IFFT and the FFT and IFFT operations, that is to convert signals and systems, and the representation in the time and frequency domain go back and forth between the time and frequency domains. Let us now, of course, that by itself has several implications for signals and system analysis. Let us now look at another interesting application of these transform domain representation, that is the matrix representation of FFT and IFFT operations in the context of something that is very interesting and relevant, and that is in a modulation technique or a waveform known as OFDM. Many of you might have heard about it. OFDM stands for orthogonal frequency division multiplexing, and this forms the basis for the high data rate transmission that occurs in your mobile phones, and even of course through via a cellular network or even via Wi-Fi in your laptop, right. So, OFDM is the dominant modulation, or one can call it as the physical layer, the signaling strategy that is employed in most modern day wireless communication systems. So, let us try to understand this better and see what is the relevance of the FFT and IFFT operations that we have just studied in this context. Okay. So, this is again a very interesting and a very relevant application of, well, IFFT, and to begin with the IFFT, and so OFDM is orthogonal frequency division multiplexing, which is the dominant, essentially the dominant for not only 4G but also 5G systems plus your Wi-Fi, for instance your 802.11n, 802.11ac, all this modern high data rate standards, right. So, enables OFDM enables high data rate wireless transmission. In fact, I might add ultra high. This OFDM enables ultra high data rate wireless transmission, and naturally this is key in modern cellular networks and as well as Wi-Fi, and the IFFT and FFT operations play a very important role in OFDM, and that is what we want to understand. What we want to explore via this module is what is the role of the IFFT and FFT operations in OFDM. And in fact, there is a reason I mention IFFT followed by FFT. Look at it, not FFT followed by IFFT, right. We traditionally think of fast Fourier transform followed by the inverse, but here interestingly it is going to be the IFFT followed by FFT, and for reasons that are going to be clear as we go through this module. So, what essentially is OFDM? Right. So, OFDM, as I already told you, enables ultra high data rates. Now, what is the problem in the wireless system? So, if you look at a basic high data rate wireless system, right, what we call as an HDR, a high data rate, right, what is the HDR what is the issue? The central issue, the fundamental problem here is HDR, high data rate, implies you have high bandwidth, but the moment you have high bandwidth, this implies small ultra small symbol time. So, it implies, so naturally if the data rate is rising, the symbol time is decreasing, right. So, this small symbol time now causes significant problems. The small symbol time leads to inter symbol interference, which is also termed as ISI. So, this is ultimately the problem, that is your high data rate leads through this chain to intersymbol interference, and naturally intersymbol interference implies distortion. And so, the long and short of the story is that is whenever you go towards a high data rate systems, the symbol time becomes very small. The symbol time, when this symbol time becomes small, the channel sort of spreads these symbols, the channel sort of smears these symbols, and these symbols start interfering with each other. That is essentially intersymbol interference, which leads to distortion. Now, once the symbols interfere with each other, naturally it becomes very difficult to recover or reliably decode these symbols at the receiver, right. So, this intersymbol interference, roughly speaking, if you want to get a physical feel for it, the symbols, you can think of it as this, as if the symbols are smeared, they interfere with each other, implies decoding is very difficult. Or the decoding error increases, right. Now, how to avoid this thing, and OFDM does precisely that. OFDM is a strategy to overcome this. So, to put it in a nutshell, OFDM is a strategy that enables high data rate transmission without intersymbol interference, and therefore, there is no distortion, and therefore, it makes reliable transmission with high data rate possible. So, what OFDM does is, in a nutshell, OFDM avoids, OFDM eliminates, I think that is implies HDR, high data rate transmission possible without ISI, and therefore, this implies no distortion. That is the advantage of OFDM. And how does OFDM do that? To understand that, let us examine the model of the wireless channel. Let us assume the output of the channel. So, what is the channel model? Let us now examine this, and this can be understood in the following simple steps. Let us start with the channel model. The channel, this is the output symbol N, right. Let us call this as output symbol or output symbol M. This can be represented as H0 XM plus h1 xm minus 1 plus so on hn minus 1 x m minus n plus 1. Now, what is y m? Y m is the output symbol. Now, this x m is input symbol at time right. Similarly, x m minus 1 is input symbol at time m minus 1. So, this is at time you have the time m minus 1 and so on, and these quantities h 0, h 1, so on h n minus 1, these are the channel taps. So, if you look at this h 0, h 1, h n minus 1, point here is that you see y m, that is a symbol at time m, depends not only on x m, but also depends on past symbols x m minus 1, x m minus 2, so on. Therefore, these symbols are interfering with each other. There is interference in x m from the past symbols. Ideally, you would like y m to depend only on x m, so that you could decode x m, but now look at this, because of the high data rate that we are talking about, y m depends on x m as well as there is interference from x n minus 1, x m minus 2, so on, that is the past symbols or the inter-symbol interference, right. So, y m, it can be seen easily depends not only on x m but also the past symbols, right, x m minus 1. So, these are your past symbols. Which means there is inter-symbol, this cause this interfere with, right. So, these interfere with x m, this implies this is precisely ISI, and this is essentially a model for your ISI channel, right. So, you have a model, this is precisely what we are calling as the ISI channel. Okay, so, this is the channel which has inter-symbol interference, your y m depends on x m and there is interference from x m minus 1 and so on. So, how does OFDM overcome this? What is the procedure that OFDM employs? The procedure is as follows. It seems a little tricky to begin with. The point is, we start in OFDM, we start with x 0, x 1, x n minus 1. So, what is the OFDM principle? And we proceed with the IFFT of these symbols. So, at the transmitter, so these are, you can think of this as the frequency domain symbols. And these are, you get the time domain samples, that is, we do not transmit the symbols directly, but perform the IFFT, unlike conventional communication, transmit the time domain samples. So, these are the time domain samples. These are the time domain samples which are eventually transmitted, but before that we have to do something else. So, the point is, from the frequency domain symbols you get the time domain samples, and this can be shown to be, the principle here is the conventional transmission. If you look at this conventional transmission, right, if you look at this conventional transmission, it can be shown that this corresponds to, this is the frequency axis, this corresponds to a single carrier transmission. That is the conventional transmission corresponds to a single carrier transmission, but in OFDM what is interesting is you move away from the single carrier transmission to essentially one that is multi-carrier. So, OFDM multi-carrier so OFDM has, so what is happening is this can be thought of as moving away from a single carrier transmission that you have in a conventional communication system, which is centered at a carrier frequency fc, to an OFDM you move to a multi-carrier system. All right, and that is the significant difference. So, OFDM is also known as an MCM system, that is multi-carrier modulation. All right, so this is also known as MCM. This is equal to multi-carrier. This is equal to multi-carrier modulation. Now, the point here is, now prior to the transmission of these samples x0, x1, and in fact, if you look at this figure n, this n has certain significance. This n is basically this number of carriers, each of these is known as a subcarrier. So, you have these multiple subcarriers now, n equal to the number of subcarriers. N denotes the number of subcarriers. So, n denotes the number of subcarriers, and what is additionally done is this interesting thing where you have x0, x1, these are the time domain samples. Now, what is samples? Now, what is done is these are repeated again, that is, you take these things from here and you prefix them. This is known as a cyclic samples. So, this is a cyclically repeated. So, it looks gives the impression of a periodic sequence. So, what you are taking is you are taking the samples, take some samples from the end, put them again in the front. So, it looks as if it is a cyclically repeated sequence. This is an important step in OFDM. This process is known as the addition of a cyclic prefix. This repetition itself is quantity that is prefixed at the head. This is known as a cyclic prefix, right. So, this process is known as the addition of a cyclic prefix, right. So, this is essentially the addition. So, cyclic prefix is also abbreviated as CP. This is addition of CP, and then follow this is the addition of cyclic prefix followed by transmission. Now, what happens when you transmit this? Now, look at this. Let us look at the output corresponding to this. So, we have y0 equals h0 times x0 plus h1 times the previous symbol, but what is the previous symbol? The previous symbol is xn minus 1 plus h2 times xn minus 2 plus so on. This would be hn minus 1 times x of you can see, not very difficult to see, hn minus 1 times x of 1. Okay. So, this is essentially what it would be, plus of course, there is going to be noise. I am not concerned about that too much at this point, that would be w of 0. Now, let us look at write one more y1 equals corresponding to the next point, y1 equals h0 of x1 plus h1 of the previous symbol, but the previous symbol is x0 plus h2 of xn minus 2, or rather n minus 1, that is the previous symbol to x0 plus hn minus 1 times x2 plus w1. Now, if you look at it, all you can see, all that has happened is x0 has moved to the right, xn minus 1 has moved to the right, everything has moved to the right, x1 from the right has come to the leftmost top. So, x1, you can see what has happened, x1 has come to the left and then x0 has moved to the right, xn minus 1 has moved. So, everything has moved progressively to one step to the right. So, you can see this is essentially a circular shift, right. So, you are taking x0, x1, xn minus 1 and you are circularly shifting this sequence. This is an important property. So, if you look at it, what is happening is you have x0, x1, x2, or let us write it this way rather, x0, xn minus 1, xn minus 2, so on up to x1. What is happening is next instant x1, or you can say x1 comes over here and x0 goes to the next spot, xn minus 1 goes to the next spot, right. So, this is your xn minus 1, so on, and ultimately here you have x2. So, this is essentially a circular shift from step to step. And it is a circular shift, it is not a push out, it is not a linear shift, because you are not simply pushing out the last one, but you are taking the last one bringing it back to the front, that is in fact your x1. So, this is a circular shift and this process is essentially what is known as a circular convolution. Now, when we represent it as a linear transform, you are going to observe something very interesting. So, essentially this is a circular convolution, right. So, every step there is a circular shift, which implies there is a circular convolution. This is not very important at this stage, because we are going to look at it in terms. Now, if you represent this as a matrix, now this can be, now let us look at what is going to be the matrix form of this, that is going to be very interesting. So, what is the matrix? The matrix form of this is very interesting. The matrix form, if you write this as y0, y1 up to yn minus 1 times, which is essentially this is the output vector, right. So, this is essentially your this is equal to a matrix times the input vector plus of course the noise vector, that is your W0, W1, Wn minus 1, right. And now if you write this input symbols, these are going to be your x0, I am sorry, these are the samples x0, x1, x2, xn minus 2, xn minus 1. And if you look at this matrix, this is going to be something that is very interesting. The first row is going to be h0 times x0, hn minus 1 times x1, hn minus 2, and so on. Last entry is going to be h1 times xn minus 1. Then your next row is going to be h1 comes to the left as we have seen, then h0 moves to the right, hn minus 1, h2, then you are going to have h2 will come from the right, then you will have h1, then you will have h0, you will have h3, so on and so forth. If you look at this, the very last row will be hn minus 1. Anyway, you do not need to worry too much about this, and this is going to be h0. Now, you see this matrix, this is, now let us look at the dimensions. This is an n cross 1 vector, this is an n cross 1 vector, this is an n cross 1 vector, this is the output vector, these are the samples, these are the transmitted samples, right, and this is the noise vector. Now, if you look at this n cross n matrix, you will observe something very interesting. You will observe that in this matrix there is something very interesting. Now, the first column, look at this, is h0, h0, hn minus 1, hn minus 2, so on. Second column, h1 comes from the right, every other element, h1 comes from the right to the leftmost spot, every other coefficient is pushed one spot to the right. Then the next row, h2 comes from the right, the rightmost to the leftmost position, and every other coefficient is pushed one spot to the right. So, if you look at it, each subsequent row is obtained by circularly shifting the previous row. In fact, same thing can be said for the column. First column is h0, h1, hn minus 1, push it down by one coefficient, bring hn minus 1 back to the top. Next one is hn minus 1, h0, h1, next one will be hn minus 2, hn minus 1, h0, h1, h2, so on. Each column is obtained by circularly shifting the previous column, and therefore, this matrix has a unique structure. This is known as a circulant matrix. This is a very interesting aspect. So, this is known as, so I am going, this kind of a matrix is known as a circulant matrix. This is a very interesting aspect. So, let us call this as your y bar, let me call this matrix as HC, let me call this as x bar, let me call this as w bar. And now, if you look at this, I can write this as y bar, in fact I can write this as y bar equal to hc times x bar plus w bar, and hc, this is a circulant matrix, which means that each row is obtained by shifting, right shifting the previous row. Each row is obtained via this is a very special matrix. We are going to discover its properties, but I am going to write this right away. This is a very special matrix, and I would like to say as a mathematician, as an engineer, a very interesting matrix. You would agree it is not every day that you see a matrix like this, right? It does not arise very naturally, right? You have every row circular shift of the previous row. So, in that sense there is only one unique row, every other row is circularly shift of the previous row. So, second row is a circularly shift of the first row, third row you get by circle. So, if you know the first row you can write down, in fact if you know any row you can complete the entire matrix. In fact if you know any column, say for the same logic, you can complete the entire matrix, and that is true because all the entries are essentially formed from the channel coefficient. So, if you know the channel filter, that essentially gives you the matrix. So, this is formed from the channel taps, right. So, this is formed from the channel taps and has a very interesting formed by the channel taps which are y0, y1 up to, I am sorry, these are not the channel taps, these are the outputs. So, these are the channel taps are H0, H1. Now, the point is, the other minor point here is what happens if the number of channel taps is not equal to n, the number of subcarriers. Typically, the number of channel taps is much smaller, the rest are replaced by 0. So, you simply 0 pad, right. So, if in case you are wondering, if you know a little bit already about OFDM and if you are assuming that you know the number of subcarriers is usually about of the order of hundreds, channel taps might be of the order of tens, the rest of the channel taps can always, I can always replace them by zeros, okay. So, it is known as, so to make things simple, I have simply assumed that the number of channel taps is equal to the number of subcarriers, but this is in no way a limiting assumption, right. This is essentially something that is, I would like to say, a generalized or a simplified, depending on which way you would like to, or which viewpoint you would like to take, okay. Now, this matrix, but our bone of contention, or our gaze at this point rests, or gaze is transfixed on this matrix, this wonderful matrix, I would like to say, which is, and I cannot talk enough of this. This is this circulant matrix. I think I have already said it a couple of times, because it has indeed, if you look at it, a very interesting structure, and this structure has and naturally you see, when you see things that are cycles, when you see things that are periodic, like cyclic means nothing but essentially cyclic has essentially some relevance to this notion of periodic, right. The moment you say cycles, remember what is cycles? Cycles is nothing but a unit of frequency, right. Cycles per second, something is cycling. So, cyclic naturally means there is something that is periodic, and periodic naturally must inspire in you as an engineer, no matter which field of engineering or science management you are from, the Fourier part of your brain, the thing that talks about sinusoid, sines and cosines, because if you think of periodic waveforms, the fundamental waveforms that come to your mind are basically sines and cosines. In fact, every other periodic signal can be expressed as a linear combination of these sines and cosines. That is the wonderful thing that Fourier theory or harmonic theory tells us. The moment you have something that is cyclic, something that is periodic. So, naturally the IFFT and FFT have a very important role to play in this system. Now, what is that role? That is something that I would like to keep aside for the next module. So, we will stop here, look at this structure of this cyclic matrix, appreciate it, admire it, try to assimilate it, try to understand it. Of course, we are going to dissect it and we are going to scrutinize it at much greater depth in the subsequent modules, and all this naturally ties into OFDM. Thank you, thanks very much.